Theory of machines and mechanisms. Mechanism versus machine. Mechanism. An assembly of rigid or resistant bodies connected together in such a way that the motion of one link causes a completely constant and predictable motions to the others. Its primary function is to transmit or modify motions. Example, slider crank mechanism, typewriter, spring-loaded toys. Machine. A mechanism or a combination of multiple mechanisms which in addition to impacting specific motion to its parts, transmit and modifies available mechanical energy into useful laser work output. Rigid versus resistant bodies. A rigid body. A body that undergoes no structural distortion or deformation under action of external forces. Resistant body. A body that is not perfectly rigid but acts as a rigid body for specific purpose of load path it serves. For example, a belt drives in is flexible fundamentally but acts as a resistant body when subjected to tensile force to transmit torque. Types of constant motions. Kinematic links must exhibit predictable behavior. The three core classification of constant motions include completely constant motions. The motion between two elements of a pair takes place in a definite single direction irrespective of the direction of the external force. Example, a square bar sliding inside a square hole. Successfully constant motions. The motion between elements is theoretically possible in more than one direction, but is a force to occur on one single direction through the utilization of external means. Example, a shaft inside a footstep bearing held down by an external load, an engine piston reciprocating within a cam and follower system kept in contact by a spring pressure. In completely constant motions, the relative motion can take place in more than one direction on reacts under reaction and its exact path depends completely on the direction of the applied force. Example, a circular shaft positioning within a loose round bearing. Classification of kinematic pairs. According to nature of contact, lower pair. Lower pair, the two elements have a surface or area contact during relative motion. Example, a knot turning on a screw, a shaft rotating inside a journal bearing, and all joints within a standard slider crank mechanism. Higher pair. The two elements share a point or line contact during relative motion. Example, a wheel rolling on a flat surface or a calm and polar pair. According to nature of mechanical constraint, closed pair. The elements of the pair are held together mechanically. Contact can only be broken by mechanical structural failure of at least one member, open or unclosed where. The two links are held in contact by external force pathway such as gravity or spring-loaded force. Example, a classical cam and polar setup. All lower pairs are found fundamentally classified as closed pairs. Kinematic pairs according to nature of relative motion, sliding pair. Links exhibit pure linear sliding motion relative to one another, matching rectangular rods, matching rectangular prisms, and whole assembly. Turning pairs, one link executes pure turning or revolving motion relative to another circular shaft revolving in journal bearing. Rolling pair, the link experience pure rolling contact without slipping. A rolling wheel on a flat surface, ball and roller bearing. Screw pairs, helicals. Matching links execute concurrent turning and sliding relative motions leads to knot assembly. Lathe machine. Spherical pair. Spherical link turns fluidly inside a fixed spherical envelope, ball and socket joint. Cast steering linkage. Type of joints and multi-link connections. Binary joint, where exactly two links are connected at a single joint node. Ternary joint where three links are connected at a single node, and ternary joint is a mathematical equivalent to two binary joint. Quaternary joint where four links meet at a single node, it is mathematically equivalent to three binary joints. Theoretical machines and reference one. General node theorem. If n links are concurrent connected at a single joint node, the connection is structurally equivalent to n minus 1 independent minor joints. Mobility and degree of freedoms. The degree of freedom defines the minimum number of independent coordinates required to fully dictate the spatial or planar configuration of a mechanisms. Degree of freedom is equal to 6 minus number of constraint boundaries. The number of restraints for a valid joint can never be zero, which imply a completely disconnected system, and can never be six, which imply a completely frozen monolithic rigid object. Three-dimensional space mechanism. For unconstrained space mechanisms, mobility is calculated using the generalized criteria f is equal to 6 whole L minus 1 minus 5p1 minus 4p2 minus 3p3 minus 2p4 minus p5, where L total number of link and Pn indicates the number of pairs possessing n degree of freedom. Planar mechanism 2D Kurzbach criterion for standard mechanism operation purely in a single two-dimensional plane f equals 3 whole L minus 1 minus 2j minus h. L total number of links in the planar layout. J total number of binary joints or 1 degree of freedom lower pairs. H total number of higher pairs 2 degree of joints. Grubler criterion for planar mechanism for standard system design with a single degree of freedom f equal to 1 and 0 higher pairs h equal to 0. 3l minus 2j minus 4 is equal to 0. Minimum link rules. All standard kinematic driven mechanism must contain a minimum of 4 links. Structural behavior based on mobility score F0 standard rigid frame or determinant structure. F less than 0 redundant frame or indeterminate superstructure contains internal pre-stresses. F greater than 0 kinematics ready operational chain. F is equal to 1 is constrained. F greater than 1 is unconstrained or requires multivariable inputs. Structural behavior based on mobility scores. F is equal to 0 standard rigid frame or determinant structures. F less than 0 redundant frame or indeterminate superstructure contains internal pre-stresses. F greater than 0 kinematic ready operational chains. F equal to 1 is constrained. F is less and is unconstrained requires multivariable inputs. Kinematic chains and structural formulation. A closed loop of link where the relative motion between the component is either completely or successfully constrained is called a kinematic chain. Testing configuration can be governed by analytical link to pair equivalence equations. Link pair relations. L is equal to P minus 4. Joint link relations. 2J is equal to 3L minus 4. If LHS is greater than RHS, lock chain structural frame, no relative motion is permitted if LHS equal to RHS. Constant kinematic chains yield predictable single input mechanical motions. If LHS less than RHS on constant chain or indeterminate loop on predictable motion. 4-bar linkage mechanism and Grasshopp's law. Grasshopp's criteria dictates the rotational behavior of basic 4-bar link based on absolute geometric parameter S length of the shortest link, A length of the longest link, PQ length of the two remaining intermediate links conditions. S plus L is less than equal to P plus Q, crank rocker, double cranks, input, grasshopper types, double rocker, strict inequality. S plus L is less than P plus Q. Double crank, condition shortest link S is fixed. Resulting class double crank, both the driver and driven link can perform full 360 revolutions. Crank rocker, condition link adjacent to S is fixed peer Q. Resulting class crank rocker One link completely a full circle while the others oscillates. Rocker condition link opposite to S is fixed. Rocker both connected links are limited to simple oscillation paths. Flat equality S plus L is equal to P plus Q. Distinct length behaves identical to case 1. Parallelogram compression S is equal to PL is equal to Q. Yield content crank rocker rotational pathway. Deltoid compressions fixing the shortest link S or longest link L provides a double crank mechanism. Fixing adjacent combination yield a crank rocker mechanism. Non-Grasov chains S plus L is greater than P plus Q. Grasov law is violated. No link is capable of performing a full 360 rotation. This systematically results in a rocker mechanism, regardless of which link is selected as ground. Kinematic inversion summary. Inversions of 4-bar chains. Crank, or double crank coupling rod of locomotives. Crank, rocker, beam engine systems, rocker, watch indicator mechanisms, straight line mechanism reference, approximate straight line, watt indicator, modified Scott Russell, Russell mechanism, straight line, Fusilier mechanism, hard linkage, classic, Scott Russell mechanism. Inversion of single slider crank chains, link one cylinder frame fixed, reciprocating engine air compressors, link to crank fixed with over quick return mechanisms, rotary radial aircraft engines. Link 3 connecting rod fixed crank and slotted lever quick return mechanism oscillating cylindrical engines. Link for slider fixed hand water pump bull engine configurations. Unique engine slider position bull. Mechanical advantage and toggle positions. Mechanical advantage. Mechanical advantage describes the force or torque amplification factor achieved by given linkage configurations. Mechanical advantage of 400% efficient losses system. Assuming a 100% efficient losses system where power input equals to power output T2 omega 2 equal to T4 omega 4. Mechanical advantage output force or torque by input force or torque T4 by T2 equal to omega 2 by omega 4, where gamma represents the transmission angle between the coupler link 3 and output crank link 4.